Okay, so remember what we are doing? We are talking about continuity, right? Continuity. And the last thing that we talked about was what I called the alternate definition of continuity, right? What's called the topological definition of continuity, saying that you're continuous on a set if and only if, whenever you take an open set in the target space and pull it backwards, then the pre-image is also going to be open. Okay, and so that's where we stopped. And you notice in the book there's a corollary, an immediate corollary, that if it's the same thing for closed, right? That the pullback of a closed set is also going to be closed. So today we're going to talk about the interaction of continuity and compactness. Continuity and compactness. Okay. So let's start off with a definition. A simple one. You have some function going from a set into Euclidean space. If there exists some number such that the absolute value of f of x is always smaller than that number for all x in your set, then we say f is bounded, right? F is bounded, right? F is a bounded function. That's sort of obvious definition. And the size of the output is controlled, right? It's smaller than some fixed value. Okay. And we're actually not going to use that definition yet, so just keep it in your mind. Let's get to an actual theorem. So suppose you have f going from x to y. These things are metric spaces. F is continuous and x is compact. Okay. Then f of x is also compact. Okay. So the continuous image of a compact set is compact.
So Professor, does it mean that f of x lies in y?
Yeah.
Okay.
Yeah, f of x is the set of all outputs. Right? You look at the image and it lies in y. Okay. Okay. So so here you have some picture. Here you have some set x, right? And you have some metric space y, right? And you have a continuous function f. And what we're saying is that the image is the image of this thing, f of x, is still going to be compact. Okay. Okay. So the proof of this is so let's think what we need to do. We say, okay, we want to show that this guy's compact. So what's the first line? Take any open cover. Pick an open cover. Pick any open cover. I usually call it G alpha, right? G alpha of f of x, right? We want to show that this thing has a finite subcover, and how do we do it? Well, we've got x is compact, right? So what do? We take that cover. We've got this cover of f of x, right? We want to show that this finite subcover. So we've got that x is compact. So we use our, what do?
Pre-image.
We pull back, right? Use the pre-image. We take these open sets and pull them back to here, right? We get an open cover of x. X is compact, so there's a finite subcover of it, and then just use the corresponding guys back here, and those guys cover the image. Okay. Should I write it up? I'll write it up. Okay. So pretty straightforward. Pick any open cover of this. Since f is continuous. So the union of the f inverse G alphas is an open cover of X, right? X is compact. X is compact. So X is contained inside some finite subcover F alpha 1, F inverse G alpha n. Right? We have some open cover. Well, X being compact means that X is contained. X compact means that X is contained in some finite subcover, right? But that from there, you know that F of X is contained in the union of F inverse G alpha I from I equals 1 to n, right? But that's just the union of the G alpha i's from I equals 1 to n. Yes, Susan.
Why is it that if f is not continuous, we can't say that the inverse image of G alpha is an open cover of F?
Well, we don't know it's going to be open anymore, right? The thing about remember we had this thing that F is continuous is the same thing as saying that F inverse of open sets is open. Right? Topological, something equivalent to continuity was that when you pull back an open set, you get an open set. So that's what we're using here. We have open sets covering here. We pull them backwards through the function through F. We get F inverse G alphas here.
Is there a way to visualize it?
A way to visualize it. A way to visualize it. This is it. Wait, this is not it? You guys are laughing. This is it.
Like when you pull the cover back and to show that F is continuous.
Okay, so maybe you like graphs. Maybe you like graphs. I don't know. Okay, so suppose you have some function. I'm going to make a very simple function. Okay, it's a line. Okay, and you have some compact set here, okay? You map that compact set through your function, right? And you get this thing here, right? So you say, okay, now I'm going to cover this guy. I want to show that that this guy is compact. You know, secretly I know it is compact, right? So I cover it with open sets, right? I cover it with open sets, right? And then I pull those guys backwards through here, right? And I get, you know, it's kind of hard to see, but you get guys down here.
And if F is not continuous?
That's not going to happen, right? Because you're not guaranteed that these guys will be open anymore.
Yeah.
Yeah.
Thank you.
I don't know if that helps. Okay. Okay. So the continuous, if you have a continuous function, put in the continuous image of a compact set is going to be compact. Okay. That's everybody all right with that? Any questions? Questions? Okay. So a couple of consequences. One, sort of obvious. If you have a function into Rk, okay, so function into Euclidean space, right? Then if f is continuous and x compact, then f is a bounded function. Right? F is a bounded function. Why? Why? Turn to your neighbor and explain why. Why that's an immediate consequence of the previous theorem?
It's gone. Yeah. Okay. And you couldn't.
You just need to say one thing.
Bounded. And compact sets are bounded.
Compact sets are bounded, yeah, Heine Burrell, or
Yeah.
I mean even less than that. Compact sets are bounded, yeah. Yeah. So you say, okay, well look, right, we want to show that f is bounded. Well, f of x is a compact set by the previous thing. F of x is compact, right? So proof f of x is compact in arcane. That implies that it's bounded, right? In fact, it's closely bounded, right? Okay, it's compact, right? So it's bounded, but that means that the function is bounded, right? If the image of the function is bounded, well then that means that's the same thing as saying that the function is bounded. Okay. Okay, so that's one consequence. Another one, maybe more important than that, is the so-called extreme value theorem. Okay, so if you have a function going from x into r, into the real numbers, and it's continuous and x is compact, then there exist points p and q in x such that f of p is the supremum of f of x, and f of q is the infimum of f of x. Okay. In other words, f attains a maximum value on x, and also a minimum value. Okay. F attains a maximum value on x, and f attains a minimum value on x, as long as your function is continuous and your domain is compact. Okay. You may remember that you had this when you were doing calculus. There's some theorem that says f continuous on on a closed interval AB, then f attains a max and a min. Right. So that's the version we saw in calculus, and now we've got it for just a general compact set being mapped into R. Okay. And this actually was the key, the foundation of such theorems as Rolle's theorem or the mean value theorem. If you ever wondered why Rolle's theorem was true, well, this is why Rolle's theorem is true. Mean value theorem, L'Hopital's rule, etc. So we'll actually prove those things in the next chapter. Okay. So. Okay, so why is this true? Right? Right, so this is saying that on some AB, then if you have a continuous function, then you're guaranteed a point where the maximum is attained, you're guaranteed a point where the minimum is attained. Right? That's not true if your function is if you're on an open set, right? If I'm on AB open, well, you could have something like this, right, where your maximum and minimum are never attained. So it doesn't happen. Okay. Okay. So let's prove this. Let m be the supremum of f of x, and little m be the infimum of f of x. Okay. Okay. Both these guys are in right. These are in R, right? F of x is some subset of R. Right. Okay. So M is in the closure, right, M is a limit point, right? It's either a limit point of the set or it's in the set already, right? This was a theorem that you read previously.
That one is closed, is it so?
I'm sorry?
But the image is also closed.
Right. Okay. M is in the closure of f of x, right? But f of x is compact. Right? F of x is compact, so it's closed. So that tells you that M lies in f of x itself. Right? Because the closure of a closed set is just the set itself. Right? So what does that say? That you attain the supremum, right? Thus, M is attained. Okay, and similarly, for little m. Oh yeah, Nick.
Why do we need the image to be like a subset of reals?
In order to talk about supremum.
Oh, so like can it be just like any ordered field with the
With a
like this upper bound property?
Well, you need to have a metric on your field, right? So no.
Okay.
No. Yeah. Okay.
This should be true for R to the K, right? The extreme value. Because you're not using anything particular about R here.
I don't know, actually. I'm not so sure. Because when you're talking, what do you mean by the supremum, right? You mean actually the supremum of the absolute values, right?
Well, yeah, you could, as a bounded, not empty subset of Euclidean space.
Yeah, but what do you mean by supremum, right?
Yeah.
Right? It's not so.
It's not clear,
Yeah,
exactly.
not so simple.
But as long as you have a distance, you could still define the notion of a supremum on a Euclidean space. Absolute value being the normal.
Yeah. So not.
It's not,
Yeah, not so simple. I'm just worried that there may be some pathological example that shows that doesn't work. Yeah, those of you who like pathological examples, I suggest the book Counterexamples in Analysis. It's really entertaining. Okay, because it's just a collection of I think the counterexamples in analysis. I think the authors Gilbaum and like Olmsted or something like that. Yeah, it's just these things that really bizarre things that people made up to show that something was not true. Sorry, okay, I'm not going to say what I'm going to say. What I was thinking I was going to say. Okay. Okay, let's go on. So, okay. So the next theorem says the following. So if you have a function from x to y, f is 1-to-1 and onto, so that f inverse is well defined. if f is continuous and x compact, then f inverse is also continuous. Okay, so the inverse function is going to be continuous. The inverse function is also going to be continuous. Okay. Okay, so the proof of this is pretty straightforward. You just want to show that it suffices to show that if V is closed in X, I'm sorry, V is open in X, then f of V is open in Y. Right? Because you need to show that when the inverse function pulls this guy back, then you get, it takes open sets to open sets, right? But that's the same thing as showing that the forwards function pushes open sets to open sets. Okay,
Is that a V?
that's a V.
Is that just any open set?
Yeah, if V is an open set, if V is any open set in X, then f of V is an open set in Y. Okay. Okay, but this is pretty straightforward, right? Because if V complement, since V complement is closed, it's compact, right? It's compact, and then f of the complement is also compact, right? Because f is continuous, right? But then, and f of the complement is the same as f of the complement, right? Right? Compact and thus closed. Thus closed, right? And so that gives you that f of v is open. Yeah, Lara.
Professor, are all closed sets compact?
Why is this closed set compact? Why is this closed set compact? Well, we've got it's closed and our whole space is compact, right? So we've got a closed set sitting inside a compact set. We had this thing earlier. Closed inside a compact means that you're compact, right? We also have a theorem that if you're compact, then you're closed. That. Okay. 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 Any questions about that? Yeah. All right.
It might be very straightforward, but how do you say the thing about the complements?
Since f is a bijection. Yeah. So since f is 1 to 1 and onto, this is going to happen. Exercise. It's a pretty straightforward thing to show. Yeah, but that's where we used the 1 to 1 and onto. Okay. Okay, I'm going to erase this because I need a full board. Okay. Okay, so now let's get to something that, you've seen a lot of these ideas in calculus before, but here's one that you haven't seen, the notion of uniform continuity. I guess many of these things you have not seen in calculus before. Here's one that you definitely haven't. Uniform continuity. So here, let me get the definition. So you have some function between metric spaces. Okay, and you have the following property. So if for every epsilon greater than 0, there exists a delta such that whenever the distance in x between p and q is less than delta, the distance in y between the images is less than epsilon, then we say f is uniformly continuous. Uniformly continuous. Uniformly continuous. Yeah, Max.
Is that just saying that it's continuous over the entire domain?
No, it's a little bit different. Does anybody see the difference between continuous at every point of x? So this is not the same thing as f continuous on the whole space. Okay. Continuous on the whole space would mean that at each x in x, for any epsilon greater than 0, there exists a delta such that if the distance between x and some other point is less than delta, then the distance between f of x and f of y is less than epsilon. Okay, and it looks kind of similar, but it's actually vastly different. Can anybody see the difference? The P and Q, yeah. So the P and Q, so here, this delta is really dependent on, it's really a function of epsilon, right? It's dependent on epsilon, but it's also dependent on x.
Yeah.
Okay, this delta, if we changed our point, our delta would have to change also. Okay, we're not requiring that this delta work for every x. We just have a delta that works for that one x. Okay. Here, what we're saying is that given an epsilon, there's a delta, right? And this delta, what does it depend on? Well, it depends on only epsilon. Okay, depends on only epsilon. So there's a delta that works for all points. Okay, the delta works for all points. Okay, so just to give a sort of a dumb example, this guy is uniformly continuous, right? This guy is uniformly continuous. Let's say that the slope is 1, right? Because if I give an epsilon of 1, you're going to give me a delta of 1. And that delta of 1 works everywhere, right? I'll say, look, if I take any 2 points whose distance is less than 1, well, then their outputs are going to be less than 1 apart. Okay, right? But if I look at, say, 1 over x, well, this guy's not uniformly continuous, right? If I say, okay, look, I give you an epsilon, I give you an epsilon of 1, say, epsilon of 1, and at this point, you say, okay, I've got an epsilon, maybe at this point, at this point, I want you to stick between here, and you give me a delta, right? That works, but that delta doesn't work for this point, right? As I get closer to the origin, my deltas have to become smaller, right? My deltas are going to change, right? So you see, the delta is related to the slope, and the slope, becomes infinite. Okay, so the delta changes. Okay, so uniform continuity means that there's a delta that works for everybody, for all points, right? Okay, so now let's get to the theorem. And guess what I'm going to say? That theorem, F continuous. So F, again, in metric spaces. You don't need to write that every time. F continuous and X compact implies F is uniformly continuous. So being continuous on a compact set means that you're uniformly continuous. Okay. Okay. Okay, so here's the picture. As usual, there's a picture. So here's your two vectors, here's your two metric spaces, x and y, and somebody gives you an epsilon. Okay, here it is. Somebody gives you an epsilon and says, I want you to find a delta. I should make this guy compact. Now he's compact. Okay, so I want you to find a delta so that any 2 points of distance delta in x are going to be of distance epsilon, smaller than distance epsilon in e. Their outputs will be smaller than distance epsilon in e. Okay. Okay. All I know is that x is compact and f is continuous. Okay. Okay. Well, f is continuous at every single point, right? So you say, okay, I know that if I take some point here, well, here's the image of that point, and I look at the epsilon ball here. Okay, so look at the epsilon ball. Okay, for reasons that will become clear soon enough, I'm going to look at the epsilon over 2 ball. So I take the half ball there. I shrink that ball by a half. So epsilon over 2. Okay. Okay. So then I use continuity. I'm going to use continuity. And I say, okay. By continuity, I know that there's some delta. I'm going to draw the big, just for ease of viewing. I know that there's some delta, so that this delta ball gets mapped inside the epsilon over 2 ball. Yeah. Okay. I know that there's some delta that maps this, so that this ball is mapped by F inside the epsilon over 2 ball. Okay. My delta is dependent on P. Okay. My delta depends on the point. Okay. Okay. And then I'm going to shrink those guys again by half. So I shrink those guys by half, delta, a half delta P. Okay. So now, and these are the things I'm going to use as my open cover. Okay, you know that there's going to be some open cover involved. This is going to be it. Okay, so I'm going to cover X with this open cover. Okay, so let me write it out. And it turns out that so what's going to happen, of course, is that you take a finite subcover, right? So you covered all of X with these half delta P guys, right? And so and then you take the smallest of those things, okay? And that delta will be the delta that works for this epsilon. Okay, that delta, the smallest of the finite number of delta P's over 2 is going to be the delta that we desire. Okay, so let's write it out. Fix epsilon greater than 0. We know that since f is continuous, so there exists a delta p. So for each p in x, there exists this delta p such that f of the delta p neighborhood of p lies inside of the epsilon over 2 neighborhood of f of p. Okay, right? So the delta p, right, neighborhood gets mapped inside the epsilon over 2 neighborhood here. Okay. And we shrink those guys by half. Okay. We shrink those guys by half and cover the whole set by that. Okay. So cover each P with a neighborhood of radius delta P over 2. Okay. Right. That's an open cover of X. Okay. X is compact. So there exists a finite subcover, right? X is contained in delta P1 over 2 P1 union delta Pn over 2 Pn. Okay. And then, like I said, let delta be the minimum of those half delta P's. So I claim this delta is the one we want. Okay. So yeah, next.
Why did you need to do like the epsilon over 2 and delta over 2?
You'll see in just 1 second when it all works out. I was thinking of doing it without doing that and showing that showing that we'd have to go back and then divide things by 2. I don't know if that would have been better, but you know, we could have done it the wrong way and then fixed it up. but let's just do it the right way from the beginning, as if we were omniscient. Okay. But really, in reality, you know, the way you did it, the way the first person probably did it was by trying it and say, oh, I need to divide by 2 here and there, and then fix it. Okay. Okay, so what do we need to show? That if we pick any P and Q such that their distance is less than delta, we want to show that then the distance between f of P and f of Q is less than epsilon, right? That's where we want to end up. Okay, so let's do it. So pick any P and Q such that the distance between P and Q is less than delta, right? P lies in some in one of those neighborhoods, right? Remember, we covered X with the finite subcover. P must lie in some element of the finite subcover, right? From the finite subcover. Okay. Okay. But remember that this delta is less than or equal to delta P over K over 2, right? Because it was the minimum of the half radii. Okay. Okay. So what am I going to say? Well, then the distance from P to P sub K is less than delta pk over 2, right? And the distance from Q to pk is less than the distance from P to pk, sorry, the distance from P to Q plus the distance from P to pk, right? Which is less than delta plus, so it's less than delta pk over 2 plus delta pk over 2, namely delta pk. Right? Right? And so, so the distance from f of p, let me write it up here. So the distance of f of p to f of q, using the triangle inequality, is less than the distance of f of p to f of pk, plus the distance of f of pk to f of q, right? But what am I going to say? This is epsilon over 2, right? So this is less than epsilon over 2, plus epsilon over 2. Which is epsilon. Let me draw a picture, and maybe that'll help clear up this last part. So you've got your P and your Q. Okay. You've got your P and your Q, and P lies close to some pk, right? P lies in the half, right? In the half neighborhood of that, right? But the distance from P to Q is smaller than delta, right? This distance is smaller than delta, right? Which is also smaller than half of that, right? So that means that Q lies in the double ball, right? Q lies in the double ball, the delta pk ball, okay? Right? So they both lie in the delta pk ball, but that means that their distance, the distance of their outputs to pk is less than epsilon over 2, right? So the distance from each other is less than epsilon, okay? Right? Remember what the delta pk ball was, right? The delta pk ball was the thing that mapped inside of the epsilon ball of f of pk, right? No. Epsilon over 2 ball of f of pk, right? So each of these guys is going to lie inside the epsilon over 2 ball. Well, the most distance they can be apart is epsilon. Okay, that's the picture, and here's the verbiage. Yeah, Helen.
So you know that the open cover of X is finite because F is compact.
X is compact, yes.
So it's bounded, therefore there's a finite number of P.
No. X is compact, so any open cover has a finite subcover.
Oh, I see.
Right.
Oh, okay.
X is compact. What that means, every open cover has a finite subcover.
Okay.
Like,
Why are we looking at the minimum delta?
because we want our delta to work everywhere. Okay, we want our delta to work everywhere. If we chose it to be just one of these guys, then it would work as long as we lay close to that one point. But we want this delta to work, right? We want this delta to be so that P and Q are going to lie inside the delta ball around the delta pk ball of pk. If we didn't do this, then this delta could be too large, right? This delta would be too large, and although P would be close to pk, Q would not be close enough to P to ensure that their outputs are within the epsilon over 2 ball. You guys don't look happy. Are you not happy? This is pretty cool. I thought you'd be kind of happy.
Sorry.
Yeah, Susan.
It is cool, but it's just kind of a little confusing. So
Yeah, that's fine.
we proved that the distance between P and PQ is less than that thing, and the distance between Q and
PK?
PK is less than that thing,
Yeah.
which is not, there's no over 2 thing. And then there, when we try to find the image,
Yeah.
the differences between
Yeah.
their images.
Yeah.
How do we go from here to there? Like,
Well, so P lies in this ball, right? P lies in the ball of this radius around PK, right? So P is inside here, right? Right, P is inside this delta over 2 ball, okay? Q lies inside this this delta ball, right? But remember how we chose the delta ball. At the beginning, the delta ball is the ball that gets mapped inside the epsilon over 2 ball,
oh,
right? The delta ball is that which gets mapped inside the epsilon over 2 ball, right? So everybody in here gets mapped inside the epsilon over 2 ball, okay, right? Yeah, but P is in fact inside it's really inside the delta ball. Q is inside the delta ball. In any case, they're both inside the delta ball,
right.
right? And so their outputs both lie in the epsilon over 2 ball, so their distances must be less than epsilon.
Okay.
Right.
No, I don't have a question.
Yeah. Okay. Okay, I guess let's stop here. I was going to go on, but let's stop here. One comment on the homeworks. Try not to use the internet. Try to do everything on your own. The experience of doing your own problems and having nowhere to turn is part of the experience part of the training of being a mathematician. Okay, that is, you don't want to be like, oh, I get the answer and I just sort of copy it down. No, you have to encounter the unknown, right? The unknown. That's the point of the problems. So please, avoid any sort of reliance on others. I mean, you can talk with each other, of course, but try not to use something that's already solved. Okay, thanks.